In this series of videos, we are taking a deep dive into the development of antidepressants. While learning about the history of 3 drugs, you will exercise essential skills on themes connected to scientific discovery. If you are a pre-med college student, an AP biology high schooler, or simply someone with some biology background who's interested in learning about the science of antidepressants, this series is for you. Years of research in the science of learning have demonstrated that deep engagement with the materials is the best way to learn and retain information. So try not to just watch these videos. Jot down some notes, pause to answer the questions, and truly be here. And with that in mind, in today's video, we will examine the background of Esketamine's approval for treatment-resistant depression. Discuss considerations about different vias of administration. Acknowledge strengths and limitations of different models in psychopharmacological research. Ratify the role of rigorous study designs and results in the drug approval pipeline. Since the 1990s, the stigma around depression has slowly scaled down, and more people had access to safer treatments like SSRIs. For the most optimistic ones, it looked like we were going to move past the epidemic of depression that scared governments at the turn of the century. But as our last video started to depict, reality is never that simple. Over time, more challenges started to arise. For one, the prevalence of depression increased since the 1990s. According to the Global Burden of Disease study, the number of cases of depression went from 172 million in 1990 to 258 million in 2017. That's almost a 50% increase. In clinical practice, patients and doctors continued to swallow the hard pill that remission of symptoms was not found as easily as a Prozac ad might have suggested. First, most traditional antidepressants take between 4 and 6 weeks to start showing effects. Additionally, the process of matching a patient to a drug is rarely straightforward. Very often, this becomes a trial and error until finding a good match. As if the process isn't arduous enough, some people do not respond to them at all. That was when we started to hear more about TRD, or treatment-resistant depression. TRD is not an official diagnosis in the DSM-5, but the American Psychiatric Association defines treatment-resistant depression as a failure to achieve remission or adequate response after at least 2 adequate trials of different antidepressants from different classes, or a failure to achieve remission or adequate response after at least 1 adequate trial of an antidepressant in combination with psychotherapy. Using data from insurance companies in the US, this study from 2021 found that 30.9% of the patients treated with antidepressants had TRD. It was in March 2019 that the perspectives of these patients and the larger field of antidepressants changed, with the news that FDA had approved Spravato, a nasal spray that works in combination with an oral antidepressant to treat TRD. Being the first major antidepressant treatment approved in decades, you may be wondering what is so special about Spravato. At least in chemical terms, Spravato is not much of a novelty. Its active substance, esketamine, is the S enantiomer of a molecule that has been around for a while, ketamine, used since the 1970s as an anesthetic. When we refer to ketamine, we're talking about the racemic mixture of S and R ketamine, these 2 molecules that exist as mirrors of each other. If you need a refresher on isomers, check out the link in the description. Based on initial studies comparing the antidepressant effects of ketamine and its enantiomer, Jensen decided to proceed with the development of the esketamine molecule. This may or may not have been influenced by the fact that esketamine, unlike ketamine, could be patented. As an anesthetic, ketamine is often administered intravenously. Would that still apply to its right-handed version? Back in our first video, we talked about Lipinski's Rule of 5, which establishes a set of criteria for the physicochemical properties of molecules in drug discovery. Do you remember why they're used? These rules of thumb are used to predict the potential of a small molecule to be an oral drug candidate. The rule states that a compound should have no more than 1 violation of each of the following criteria: a molecular weight of less than 500 daltons, no more than 10 hydrogen bond donors, no more than 5 hydrogen bond acceptors, and a calculated octanol water partition coefficient below 5. This set reflects the observation that most oral drugs are small and somewhat lipophilic molecules. While this makes sense for drugs that need to cross cell membranes through passive diffusion, this is not the only way that a molecule can reach its target. While these rules do not get at whether a molecule will be pharmaceutically active, which can only be assessed later on in this process, they have proved to be good rules of thumb to filter molecules that are unlikely to be feasible as oral drugs. So now it's your turn to answer. Based on Lipinski's rule of 5, is esketamine a strong candidate? Pause the video here and use a search engine to check if esketamine meets the criteria. Once you're good to go, hit the play. By now, you would have found that esketamine has a molecular weight of 237.72 daltons. We can tell that it has one hydrogen bond donor and two hydrogen bond acceptors. Finally, esketamine has a calculated octanol water partition of 2.2. Therefore, esketamine meets all of the criteria from Lipinski's rule of 5. All good. So if esketamine is a good candidate for an oral drug, why did it get approved as a nasal spray? Other factors also determine the mode of administration of a drug, such as metabolism. When esketamine is orally administered, it is metabolized by the gut and liver into metabolites with different properties, thus reducing its availability in systemic circulation. As a nasal spray, esketamine bypasses the gut and liver, being absorbed directly into the bloodstream through the nasal mucosa. This allows for faster onset of action and more consistent levels of the molecule circulating in the body. Alternatively, intravenous administration could maximize bioavailability, but it's also an invasive and painful procedure. Thus, nasal administration is a good compromise for optimal absorption and limited invasiveness. Insights about optimal modes of administration and even hypothesized disease pathways often come from studies in animal models. Over the years, many species have contributed to this research, accumulating evidence that led to improved models of depression and opportunities for intervention. For example, in 1985, a group of scientists from the United Kingdom used thin slices of rat somatosensory cortex to investigate the actions of ketamine. It was one of the first studies to suggest that ketamine worked as an NMDA antagonist. In this other study from 1996, they found changes in binding to NMDA receptors in the cortex of rodents following the administration of different antidepressants. This strengthened the hypothesis that the family of NMDA receptors could be involved in the etiology of depression. While the mechanistic plausibility for ketamine as an antidepressant started to rise, this study from 2001 demonstrated that NMDA antagonists, such as ketamine, defied depressive-like behavior in mice on the forced swim test. You may remember this paradigm from our last video, when we talked about fluoxetine's failure to display a significant effect on this test. Obviously, these are only a few papers out of hundreds published every year. They each help push the borders of our understanding a tiny bit further, and over time may amount to things like a treatment used by thousands of people. If you've been paying attention to the experiments in the series, you probably noticed that rat brains and mice cortices were quite popular. Can you give one biological and one practical reason for this choice? Once you've nailed those down, hit the play. Even though our most recent common ancestor lived a couple of million years ago, we share many anatomical and physiological similarities. Plus, more practical aspects, such as their small size and short lifespan, along with the ease of genetic manipulation, place them as one of the strongest candidates as animal models for drug discovery. As expected, this practice comes with limitations. At the end of the day, and as shocking as this may sound, rats are still rats, mice are still mice, and humans are still humans. If this inconvenient truth is ever present in any other domain of biology, it gets even trickier when studying psychiatric conditions. While paradigms like the forced swim test are trying to get at behavioral analogs of depression, depression is not described by how long you swim before you start to float. We often struggle to define depression in humans, and it encompasses physical, psychological, and behavioral aspects combined in a variety of ways. Could it be that neuropharmacological research has grown over-reliant on rodent models? While we still need animal models to answer more systemic questions, computational models and organoids are increasingly better to experiment with metabolic pathways and connectivity. Advances in basic science can further amplify the applicability of these models, providing more granular mechanisms for how depression arises and develops. With clear causal mechanisms, the identification of biological targets can become more targeted and effective. Hopefully, this will speed up the development of antidepressants and expand the number of options for patients. The limitations in animal model research remind us why preclinical data must always be interpreted with parsimony. In the case of esketamine, some animal studies demonstrated an effect within hours of administration. But how do you think it translated into human biology? No need for a mystery, because we're moving into your favorite part of the drug pipeline process: clinical trials. In our last video, we reviewed the steps in the FDA pipeline leading up to approval and clinical use. After filing an investigational new drug application, the sponsor will proceed with studies at phases 1, 2, and 3. Each phase tries to answer different questions about the drug. Do you remember what's the goal of each phase? Here's your nudge to pause the video and think of at least one question that each phase tries to answer. When you're good to go, you know the drill. In phase 1 trials, we're often concerned with safety, whereas phase 2 trials will ask questions about efficacy. Finally, phase 3 trials have the largest and the most diverse samples to ask questions about both safety and efficacy in different populations. While all drugs need to move through this pipeline, some might make it faster than others through special designations. For example, esketamine was granted 2 designations. The Fast Track designation was justified on its potential to fulfill a gap in options for treatment-resistant depression, while the Breakthrough designation was granted on the basis of significant promise from preclinical data, showing a rapid acting effect of esketamine. These designations confer a few benefits, such as scheduling meetings with the FDA more frequently or getting a prioritized review. But as the FDA reassures us, it should not decrease the level of evidence needed for approval. This is one of the reasons why esketamine was approved under a risk evaluation and mitigation strategy. This is often requested from drugs with lingering safety concerns to monitor and mitigate risks through a set of protocols. For esketamine, this meant that the nasal spray can only be administered in certified clinical centers, and patients need to wait for at least 2 hours for close monitoring of immediate side effects like dizziness and elevated blood pressure. Can you guess when these concerns came to the attention of the FDA? And if you couldn't tell, I am a major fan of clinical trials. We're looking into a randomized, double-blind, multi-center, active controlled study of intranasal esketamine plus an oral antidepressant for relapse prevention in treatment-resistant depression. Or simply SUSTAIN-1, a phase 3 study trial from 2015. Unlike the 1959 study that we picked apart in the first video of this series, you know, the one with unclear protocols of treatment and a vague explanation of results, the title of this one gives away a lot. Patients were randomly assigned, and neither they nor the healthcare providers knew who was getting the actual treatment, which consisted of intranasal esketamine and an oral antidepressant. Those were compared to an active control. In other words, an oral antidepressant with a demonstrated degree of efficacy. The subjects were located in different care centers and had 2 things in common: treatment-resistant depression and a desire to prevent relapse. The study has a detailed explanation of treatment protocol, what oral antidepressants were used, how they got selected, and how often the subjects got the doses of esketamine. The SUSTAIN-1 trial demonstrated that treatment with esketamine resulted in a statistically significant reduction in depressive symptoms compared to the control. At week 4, the change from baseline in the MADRS total score was significantly greater in the esketamine group compared to the control. Additionally, a significantly higher proportion of patients in the esketamine group achieved response and remission at week 4. While typically the FDA will require at least 2 double-blinded RCTs in phase 3 studies to formalize approval, SUSTAIN-1 was the only one out of 5 studies meeting these conditions. This decision motivated criticisms accusing the FDA of lowering the rigor of evidence often requested from any other drug. Critics also questioned how much clinical benefit esketamine could really offer, and pointed at insufficient evidence to even weigh on this question. It's time to see it for yourself. Pause the video and open clinicaltrials.gov on a different tab. Look up the trials with esketamine and depression. You can use the filters to look at the ones that have been completed. Based on these findings, what can we confidently say about esketamine? Once you've reviewed the ground, write a paragraph to advise the FDA on how to move forward. Should eskedamine's approval be reconsidered? On what basis? And remember, these decisions have a real impact on people's lives, and we need more and more voices of critical thinkers, scientists, and citizens as part of this conversation. Okay, time for a recap. Despite an increase in depression cases and challenges with traditional treatments, the FDA's approval of Spravato in 2019 for treatment-resistant depression provided hope, as it's the first new antidepressant approved in 2 decades with promising results for a rapid effect on symptoms. We discussed how esketamine meets Lipinski's Rule of 5, making it a strong candidate for an oral drug, but that eventually got approved as a nasal spray due to considerations of drug metabolism. While preclinical data from rodent models is a valuable instrument of psychopharmacological research, there is only so much you can learn from them. This is why the next step in eskedamine's approval pipeline was clinical data. After a refresher on the FDA approval pipeline, we reviewed the importance of a clear treatment protocol and outcome analysis in a clinical trial by looking at SUSTAIN-1. Finally, you face the limitations of existing data about esketamine and weighed in on the FDA's decisions after approval. You can find all the references used to produce this video in the description. There, you can also find recommended resources that complement today's topics. See you in our next series.